should be.
Okay, so our next speaker is Yixuan Li from Munich, who's going to tell us about holography for KKLT.
All right, so thank you for the organizers for the invitation, also the commentator, of course. So yeah, today I'm going to talk about work that is going to appear soon with Joseph Bena and Séverine Lust. So that is about holography and about KKLT. We all know that the usual way, the usual paradigm from string theory to get real-world physics is through compactification, right? So to assume that we live in, we live in four-dimensional universe, but then there are like 6 dimensions that are very small. And to explain the four-dimensional effective field theory, we have to start from the 10-dimensional theory. But since the higher dimensional theory is very rich, for example, the geometry of the hidden dimensions, which is the Calabi-Yau geometry can be very intricate. On top of that, there can be very different field content, which induce different amount of fluxes. So in the end, it gives at least 10 to the 500 solutions. And the idea is to say, well, the universe that we live in is probably one of those that we can construct in this this setup. But we are in a swampland session, and the swampland session tells you that, well, actually no, there are some constraints, and the constraints are actually that first, maybe it's not possible to get scale-separated ADS vacua, and also maybe there is not even long-lived de Sitter vacua at all. So within this perspective, this framework, there is a potential counterexample, which is the KKLT proposal. The scenario, actually. KKLT for Castro, Kalosh, Linde, and Trivedi. And so the KKLT scenario is essentially a two-step procedure. In the first step, one needs to stabilize the Calabi-Yau moduli with fluxes, add some non-perturbative corrections, and then one gets a supersymmetric scaled-separated ADS vacuum, so with the cosmological constant smaller than 0. In the second step, one can raise the cosmological constant to a positive value by adding anti-D3 brane at the bottom of a warp throat in the Calabi-Yau. And so this would give a de Sitter vacuum with broken supersymmetry and of course with a positive cosmological constant. So in this talk, we will study the first step through holography and domain modes. So the idea is that, okay, we have a complicated Calabi-Yau. The Calabi-Yau has different cycles, so 2 cycles, 3 cycles, 4 cycles. And so all of these are encoded by complex structures and Kähler moduli. So the idea is that the complex structure deformations, which control the sizes of the 3 cycles, can be stabilized by fluxes. One writes a superpotential, the Gopa-Kumar-Vafa-Witten superpotential, that depends on the fluxes F3 and H3 of type 2b. Sorry. So that's the first part. Once you stabilize these complex structure deformations, you can, on top of this, stabilize the Kähler moduli. So this is the proposal from KKLT, right? And these moduli control 2 cycles and 4 cycles. And for this stabilization, this time you need some D3 and Sarton corrections. So what you need is that these exponentials to be very, very small. Otherwise, your computation is not valid. Once you get that, you can get a cosmological constant in terms of the Kähler modulus, sigma 0. And so the value of the ADS cosmological constant would be dependent on an exponential of sigma 0. And so since this exponential is very, very small, you get automatically that the cosmological constant of your ADS is very small as well. And this is what you need for the second step. So the idea here is that we want to study this from holography, and the tool to do this is to trade the fluxes of the branes. And so the idea is that, okay, well, I am on the Calabi-Yau 3. I can exchange the fluxes F3 and H3 by some D5 and NS5 branes that are wrapping dual cycles. So they would source these fluxes. And actually, there is a simpler 3D version of KKLT from M-theory. So you can be on M-theory, you compactify on the Calabi-Yau 4-fold. The Calabi-Yau forward is a kind of enhanced version of this Calabi-Yau 3. And here, the flux brain exchange would be that you would trade a G4 flux on the Calabi-Yau 4 with M5 brains on dual cycles, on the dual cycle L4 that is within the Calabi-Yau 4. So because you have a self-dual condition, the self-dual condition is telling you that locally you should have such a system like that. So the directions 1 to 8 are labeling the Calabi-Yau fourfold. You would have, so locally you would see a M5 brain self-intersecting with itself at a special point z equals to 0, and the M5 brains would have a common direction y. Because you want to have a typal cancellation condition, what you need is that on the other side of this z, you need to add some M2 brains that are also in this, wrapping this common direction. So pictorially, it looks like something like this. So at z equals to 0, you would have a domain wall that is made of M5 brain wrapping a kind of cycle, so it's a special Lagrangian submanifold, L4, within the Calabi-Yau. On the other side, so z less than 0, you would have many M2 brains that are everywhere. And far away, at z equals to infinity, that is where you see the supersymmetric ADS3 from M theory on Calabi-Yau 4 in the presence of a self-dual G4 flux. But on the domain wall, there are degrees of freedom. And the idea is that the number of degrees of freedom captures some kind of ultraviolet central charge, CUV. So this is the idea by these people, Lust, Vafa, Wiesner, and Xu. So I will refer it to the Harvard group paper. So far away from the brain, at z equals to infinity, there is a infrared central charge which measures the radius of the ADS3. So this time the CIR would be proportional to 1 over the cosmological constant. But because you would have a C theorem, you would have that the infrared central charge has to be smaller than the ultraviolet central charge. Therefore, you would have a lower bound on the cosmological constant, the absolute value of the cosmological constant. And so, in this paper, these authors estimate the central charge in the VUV by computing the number of deformations of this special Lagrangian of this domain wall. And it turns out that the result is that the central charge in the UV has to be scales like the number of flux squared. Therefore, the lower bound on the cosmological constant is that the cosmological constant has to be bigger than something of order 1 over n squared. So it cannot be arbitrarily small. However, you needed this number to be exponentially small in the KKLT scenario. So therefore, the authors claim that it's impossible to get enough degrees of freedom on the brain to get a sufficiently small cosmological constant. So now you can come to me and say, oh, but actually there may be some caveats because the Harvard group was taking a domain wall that sources the KKLT ADS, and they declared that the degrees of freedom on the UV side are the deformations of the cycle, of the submanifold, of the slag, of the special Lagrangian. So this is exactly the kind of strategy that worked for the black hole side. So if you remember, back in the 90s, there was this MSW black hole, so Malacina Witten, and so it was exactly to count what is the number of deformations of some polymorphic cycles, and then this matches exactly with the entropy of the black hole. But here we are not with in the black hole system where we can compute, where we can compare the number of degrees of freedom on the brain side with the macroscopic entropy of the black hole. So we cannot use this kind of thing, and one can come and tell you that maybe there are hidden degrees of freedom. And so in particular at the M5 brain intersections, you could have much more degrees of freedom. If I think about, for example, a D1, D5 system, the central charge is N1 times N5 instead of N1 plus N5. So you could have some kind of entropy enhancement due to that. And so here, potentially, you could have degrees of freedom that are coming from M2 branes that are ending on the M5 branes. Right. And so what we have to do is to evaluate the radius of the ADS space that corresponds to the brane intersection with the most degrees of freedom. All right, but what is the configuration with the most degrees of freedom? Well, essentially you would expect that your complicated curve, special Lagrangian, is self-intersecting everywhere along the Calabi-Yau, but you can squeeze all of the self-intersection at the same place. If you do that, then all the branes that are interacting at the same place, and so the brane interaction is enhanced. And so these are the configurations where the branes are all intersecting the same place should contain the maximal degrees of freedom. But okay, now how to get an anti-de Sitter space capturing the degrees of freedom of the intersection? Well, locally, the M2 branes, what you see is the M2 brane ending on the self-intersection of M5 and M5. What you know is that the M2 brane is going to pull the world volume of the M5 in the same way as a fundamental string would pull the world volume of a D3 brane. That's the Kalman-Anderson effect. So it turns out that there exists a solution corresponding to this intersection, whose infrared limit is the ADS3 cross S3 cross S3 warp product with a two-dimensional Riemann surface. So reading off the central charge here is, in this configuration, is a mess, but we can compute the central charge from a similar configuration. So instead of having this M2 brane ending on a very special, at a point, we can we propose to put the M2 brane charge ending on the entire M2 brane on a cross shape, and then assume that Z is compact and smear the M5 charge along Z. We can take the near horizon limit, and this would give a central charge. So since maybe I'm a little bit out of time, there exists a supergravity solution corresponding to this smeared intersection. There is a metric that is governed by some harmonic functions. And so you can go to the near horizon limit. The near horizon limit is the ADS3 cross S3 cross S3 cross T2. The two S3s, they are the S3s of the M5s. So these S3s. The ADS would be made of time, Y, the common direction, and U, which is the product of the two radii of the M5. So again, you can compute the central charge of this ADS3. This would be proportional to the number of M2 branes and the number of M5 branes. So this is proportional by using the Tadpole cancellation condition to the number of flux cubed, which is a bigger value than what was found by the Harvard group. So that means that we have a weaker bound on the absolute value of lambda due to the presence of the M2 branes on the other side. We can play the same game in the type 2b situation with the ADS4. So we can. There exists also a supergravity solution for the D5 NS5 D3 intersection, and again the solution has a near horizon limit that is of the form ADS4 times S2 times S2 warp product with a two-dimensional Riemann surface. And again, it's possible to compute the ADS radius in four-dimensional Planck units. And this time you will see that it's proportional to a number of flux power 4, essentially. This matches with the free energy of a three-dimensional CFT. And so actually you would know exactly what are the degrees of freedom in this setup. And so to conclude, we have studied local models for brane system that source the KKLT's type ADS vacua. We computed the ADS radius of the brane intersection in the UV. It turns out in the M theory configuration, we measured the radius of the ADS3, which was proportional with n cubed, and in type 2b, it was proportional with n power 4. So both the degrees of freedom, both the values are bigger than what was found by the Harvard group, which were where they were counting the deformations of a special Lagrangian inside of Calabi-Yau. And so the new degrees of freedom would correspond to some kind of Hanani-Witten-like degrees of freedom. What I mean by this is that before you would have this curve that is at z equals to 0, but actually you could decide to pull them infinitesimally away from it, and then you would have some M2 brane that appear, and so these would be the Hanani-Witten-like degrees of freedom. So, however, it's not possible to have more degrees of freedom than that because we are computing the radius of the UV ADS. And so the new bound would be something like that the absolute value of lambda is bigger than something of order 1 over n squared, n to the power 4. And therefore would get to the same conclusion as the Harvard group, which is that there is not enough degrees of freedom to get a ADS with an exponentially suppressed cosmological constant needed in the KKLT scenario. Thank you very much for attention.
Questions for Yixuan? Please.
Did the non-perturbative effects not play a role at all in this story?
No, they should. I mean, it's that I think the point is that the non-perturbative they should be counted by any the CFT in the UV. So if the KKLT ADS exists, then there should exist a CFT that captures not only the flex part but also the non-perturbative part. And yeah, what I think what we're saying is that even just the flex part is already missing.
Don't you need to include like 7 branes or something extra then, at least in the KKLT?
Well, why is that?
Because that's what's supposed to non-perturbative effects. Yeah, that's one scenario that potentially.
Yeah, but here I can consider some just Euclidean D3 branes, right?
Yeah, so I got a little bit confused because you'll need minimal supersymmetry for KKLT, and then you're using these M2, M5s or D3, D5s that have a lot more supersymmetry. These ADS3 and ADS4 vacua that you mentioned have a lot of supersymmetry, right? Like the ADS4 backgrounds have half maximal supersymmetry.
Right, but this is in the UV, so then there would be supersymmetries that are broken in the IR. I think that's the picture.
What breaks them? Like how is the claim that the putative 3D CFT dual to ADS4 vacuum is somehow in the IR of these 3D CFTs?
Yeah, I think so. I think this is what we want.
How do you know this? Like who has established this?
No, we did not establish this. So that if it exists, then we should be able to realize it as a brane setup, right? And this is the Harvard group argument. And then since they do not compute a ADS, they just have a computation on the CFT side, which is say, well, what is the worst case scenario? And the worst case scenario is when you put all of the branes together, and then you would backtrack into an ADS.
From the CFT side, that this seems like a very strong statement, and essentially rules out immediately KKLT without any of these details, right? But don't you agree that if you say that the 3D CFT putative dual to ADS4 of KKLT is in the IR of these Gayotto-Witten type theories, then game over, right?
Right. I mean, so this Gayotto-Witten guys, it
seems like a very strong statement.
Right. Okay. I don't know. We have to put it at some point in the Calabiao, right? So the Gayotto-Witten, they're in flat space, and
right,
so
which is essentially what I'm asking. How do you know that these things that have a non-compacted space suddenly are relevant for KKLT?
No, okay, maybe that is the weak point. Yeah. Okay.
Any further quick questions for Yixuan? Well, if not, then let's thank you, Marianne.